Alright, this is the final section where things make very little sense in the macroscopic world. After this, we start getting into models again and start getting into ideas of um, ways we can put things together so that we can make a little bit more practical sense out of it, ways to envision how we can use this in a more concrete manner. But for this chapter, this is probably the worst out of the set, honestly, in terms of trying to understand this on a macroscopic scale. So remember the cat, right? It's dead, it's alive. How does that make sense? Remember that it doesn't, okay? The whole aspect of what we're about to talk about doesn't make any sense on a macroscopic scale. We just have to understand that we can experimentally observe this on the quantum scale to be true, right? Because things act differently on that scale. Alright, so what's the issue here? The issue is that electrons behave like particles and they behave like waves. Okay, so we've seen some particle-like properties of electrons. You can add them to an atom, you can take them away from an atom, you can't have half an electron. That's a particle-type property, right? Now remember diffraction, where things go through an opening, waves spread out where particles go straight through. And remember how when waves intersect on each other, they amplify if they're in phase and they go away if they're not in phase. Well, we can put waves through two openings, and then these circles will start to intersect with each other. And as they intersect with each other, they'll start to amplify and make bright spots on a wall farther away from yourselves. This is where we're looking at light here. And on places where they intersect with each other in a destructive way, out of phase, you'll get dark spots where the light doesn't hit. So effectively what you get is referred to as this diffraction pattern. This idea that the light will interfere with itself constructively in phase and destructively out of phase to give a kind of alternating set of light and dark spots if it acts like a wave and it's traveling through two openings. Okay, so what about electrons? If we aim an electron's emitting source at two slits, we can see what happens. What we expect to happen if it's a particle is it'll either bounce off or hit the slits. If it hits the slits, it goes through. So therefore, the only place we should see a bright spot on a film that's detecting the electrons is right in the same path as the two openings. What do we actually see? Well, what we actually see is a diffraction pattern. Okay, so think about what that means. That means that the electrons are seeming to act like waves. But we already know they have particle-like properties because we can add and subtract them from individual atoms. Well, this is where it gets really weird. The physicists that looked at this thought, well, maybe the electrons are just bouncing off each other. We're sending a lot of them through at once. Maybe the bouncing is causing a distribution of locations. So let's reduce this to putting one electron through at a time. Well, the weird thing that happens is we can record this over time and record where they hit, and as you put enough electrons through, one at a time, so they can't be bouncing off of each other, we still get a diffraction pattern. So it's still acting like a wave. All right, well, how can this possibly make sense? The electrons have to be exhibiting wave-like properties in order for this diffraction pattern to occur, right? But you're going to probably tell me, all right, so the waves have to interfere with each other, though. There's only one electron. How can they interfere with each other? Well, the really strange thing is being quantum-sized, the electrons, just like all the quantum stuff we talked about way at the beginning of the chapter, in the whole cat issue, quantum-sized things can exist in multiple states at the same time. Okay, so what does that mean about the electron? Well, the only way that this makes sense, the only way that it makes sense at all that we're seeing this diffraction pattern when we send the electrons through one at a time, is it means that the same electron went through both slits at the same time. That's the only way this makes sense. And what that means is it went through as a wave, and it then interfered with itself on the other side, as if it was going through both slits at the same time, but still somehow interacting with itself as one object and two objects. You remember the cat. It doesn't make sense. It doesn't make sense on a macroscopic world because nothing we observe in the day-to-day life does anything remotely like this. If I walk through a door, I walk through a door. If there's two doors, I don't walk through both doors and then bump into myself on the other side. It doesn't happen. But on the quantum scale, it does. Well, of course, YouTube is a wonderful resource, so let's watch a quick video. It's a couple of minutes. It has all sorts of great animations, shows the insanity of this, and does a much better job than I can.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this?
All right, so now we know more about electrons. We know that they're both a particle and a wave, and we know the other mind-boggling aspect of this is that we can't observe both properties at once. If we observe the electrons, we get rid of the chance for the cat to be both alive and dead at the same time. We force it to be one or the other. In the slit experiment, double slit experiment, what that means for us is if we observe the electron, it goes through one side or the other, not both, and all of a sudden starts behaving like a behaving like a particle. And if we remove the observation ability to determine whether it went through one side or the other, all of a sudden it goes through both again. Quantum insanity. All right, so taking for granted that electrons are waves and particles, let's look at the wave properties of particles. They have experiments that were able to determine the wavelength and the relationship between the wavelength of electrons or particles in general. But this really only applies to things that are so incredibly tiny that you have an appreciable wavelength to them. And electrons are small enough that if we look at the wavelength and how it's related to the object's characteristics, the mass and the velocity of an electron are such that we combine this with Planck's constant, which is very, very small amount of energy times seconds. We can actually get an appreciable wavelength. And for electrons traveling at normal electron type speeds, we get a wavelength of about somewhere around 0.2 nanometers. And so, I mean, remember from the whole light side of this stuff that we talked about already, this is somewhere, in the ultraviolet range of light. That light travels in that sort of a wavelength. So electrons have a real appreciable wavelength, especially considering their size. Now, on top of this, since we have this particle and this wave in one, the same electron can act like either, we have an issue with knowing things about that particle, which leads to the Heisenberg uncertainty principle. And of course, we can't mention Heisenberg without mentioning the only chemist that you really ever see outside of CSI Miami on television. But the gentleman here from Breaking Bad, if you didn't recognize the picture, I've seen the series. But the Heisenberg that he stole that name from came up with this way to define the fact that the velocity being a wave aspect of the electron and the position of the electron being a particle aspect of the electron, we can't actually know both of these things infinitely well at the same time, because the electron will not act like a particle or a wave simultaneously. It only acts like one or the other. So if we try to measure a property of each, we're stuck with getting really well-defined measurement of one property but not the other, or vice versa. So the equation tells us that we can tell where it is, or we can tell its velocity, or its momentum here, it's mass times velocity. But the two are related in a way such that we can't know their, this change means that we're measuring it here. We're looking at the change in position or the change in velocity. We can't know these two aspects infinitely well. They're directly proportional to, indirectly proportional to each other, meaning that the more we know about the change in position, the less well we know about the change in velocity. The better we know the change in velocity, the less we know about the change in position. And this is all related nicely to Planck's constant again, a couple other constants, 4 pi there at the bottom. But the overall take-home message I want you to get from this is just this. The more we know about the position, the less we know about the velocity, and vice versa. Alright, so if we don't know the position infinitely well and the velocity infinitely well at the same time, how does this work? Well, with classical physics, like I throw a baseball or I throw a hammer up in the air or something like that, it's going to follow a specific path. And that path I know by its position and by its momentum. What forces are acting on it and where it is right now. So that's classical physics. I can measure both of those things to such a high degree of accuracy that I can assume to know both at the same time. But on quantum physical levels, we can't know the position and the momentum at the same time. So what we're limited to is kind of knowing a probable distribution of where that object will be, knowing where it was and where it was going. So instead of a particle where you throw a ball and you know where it's going to end up because you threw it with a certain amount of force in a certain direction at a certain time, with electrons, you can only kind of guess that they're going to be somewhere within a certain area or volume of space. And that's about as close as you can get to electrons. So what's coming up next in the subsequent sections now is we're going to start talking about where electrons specifically are around an atom. And they're not in little orbitals, they're actually in probability distributions, areas where electrons are likely to be. And we're going to draw these out in little three-dimensional volume shapes with higher probability areas indicated by darker shading. And so that's the take-home message of this part of the chapter.